Hello, everyone. Uh, Hello, everyone. I'm Amine-based Research Fellow at the University of Surrey. It's my pleasure to be the chair of another session dedicated to early career researchers that works under umbrella of AI for Net Zero, which stands for Artificial Intelligence for UK Zero, that funded by UKRI. So today we are delighted to host two speakers, that Dr. Mengjia Zhu from University of Manchester, and also Dr. Florian Baakes from Imperial College. Please join me welcoming them, and feel free to engage anytime in discussion by writing your comment and question. We have 10-minute Q&A at the end of the talk as well, so you can leave, leave your comment for that time as well. Before we start the first talk, let me remind you that to leave your comment, you need to log on your Google account. I need to say that for today's meeting, Professor Ahmed Sheikh also helping me for co-chairing this session. Hello, Ahmed.
Hello.
Sure. So without any delay, let me introduce our first speaker of the day, Dr. Florian Baakes. He is a postdoctoral research associate at the Imperial College London, working on the EcoAI project, which applies machine learning in the context of carbon capture and storage. He holds a PhD in electrical engineering from the KIT Germany, where his research focused on developing mechatronistic models for thermal runaway in lithium-ion batteries. He aspires to advance sustainable energy by designing efficient and innovative process and system, especially in carbon capture and battery technologies. So thank you to joining for this session, and floor is yours, Florian.
Well, thank you, Amin, for this very kind introduction. I really hope you all can see me and my presentation. And as already introduced, I'm working at the Imperial College in London, and my work is basically positioned in the EcoAI WP2 work package, which deals with applying machine learning models in the context of carbon capture and storage. So my talk today will deal with how we could use machine learning models in the process design of an amine-based carbon capture model. Just to give a short reminder why all of this is so necessary, like 51 billion tons of CO2 equivalent are released to the environment by us humans annually, which has these catastrophic effects of increasing flooding, storms, and droughts, and everything then comes afterwards. And 3/4 of that CO2 equivalent tons are attributed in one or the other sense to energy, if it's used in industry, for transport, or in buildings. And if we now consider more conventional procedures to process, like to create energy, such as coal or gas-based power plants, we already know that the flue gas contains quite a lot of CO2. So the idea to simply capture and store, or even better utilize it, is actually very brilliant. However, the energy that we need to capture and store it is quite high. So we have a parasitic power demand of 20 to 30%, which will reduce the amount of power that we can produce with the power plant, which then in the end increases the process costs. While this definitely will lower the incentive of everyone running a power plant to employ the carbon capture procedures. So in optimizing these kind of processes to lower the costs is definitely a goal that we should follow. Now, let me introduce you to the process that I will look at today, or I will introduce you today, which is an aqueous amine-based carbon capture process. And here you can see a typical flow sheet of these kind of procedures. And here you can see on the lower left corner of the diagram, the flue gas, like the CO2-rich mixture that enters the process, which might be a combination of carbon dioxide and nitrogen, or nitrogen and oxygen, depending on the flue gas that we are considering. And on the top right-hand side, we see the mixture of our solvent. Here I show you methyl ethanol. amine, which is more or less the gold standard right now, where already some of CO2 is attached to it based on previous loops. And in the very first stage now, we have to bring our gas and the liquid phase into contact, which then allows the CO2 to be like absorbed or captured by the amine molecules, which then separates it from the vapor phase or the gas phase, which is then free to leave to the environment because it does not contain the CO2 anymore. The CO2-rich liquid phase then is transported to a heat exchanger to the desorber, where we increase the temperature of the liquid mixture, which loosens the bond and then helps us to separate the CO2 from the liquid or the amine again, which allows us to store it and hopefully later utilize it, or simply to store it and mitigate the effect it could have on the climate. Then the CO2 lean or CO2 core phase is again transported to the same heat exchanger, giving back some of the heat it got before in the desorber to the rich mixture and entering the absorber again, so we can repeat the process with the same mixture. Now, the question arises, what can be optimized considering these kind of processes? So a known variable that we can optimize is the lean loading. So how much of our CO2 is already attached to the MEA once it enters the absorber? Another very direct thing to think about is the column sizing. So how big does our process really need to be in order to work? As the pressure in the desorber is an important variable, and the absorber or the inlet temperature of the absorber can be considered. But this is only dealing with the process conditions. And if we actually think about the whole process, we could also deal with the molecule itself, so the solvent molecule, what kind of solvent molecule we want to use in the process. And here are we would have several choices. Just to name a few, the already introduced MEA, which is more or less a gold standard, at least in academia and industry right now. And but there are several other ways, such as like DEA or MDA or MPA, and this already is a very, very, very small part of the whole solvent design space. So in an ideal world, or the overarching goal of our projects actually, is to use machine learning in a solvent, like an integrated solvent and process design, where we optimize both together. However, for today's talk, we are not quite there yet. So I'm focusing on the implementation of the machine learning models for an MEA-based process, and then a little bit discuss how that would extend to use it in a solvent integrated solvent design problem. Now, the next question that arises, why machine learning and how can it help? Well, these integrated solvent and process design problems can be very, very complicated and rather slow, and also might not lead to a robust conversion of the optimizer. And what we promise ourselves while introducing machine learning, which is also quite known, is that it should be faster than the model that we are replacing, and hopefully also more robust, which is something that I will discuss or try to discuss later a little bit. So after discussing why we want to do it, the question now arises how we can do it. So there are several ways to introduce machine learning models into the process optimization, one of which would be a process surrogate, where we replace the whole process by a machine model and then optimize our surrogate. And another way would be a unit surrogate, where we replace a unit, or a property surrogate, where we replace property calculations, such as, for example, viscosity, surface tension, or in this case, the flash calculation, or the calculation of the equilibrium. So how do our molecules distribute between the liquid and the vapor phase, which is obviously a very important attribute in this kind of processes. Since I already introduced that the overarching goal would be to go to solvent design problems, the process and unit surrogates do not really make sense for our kind of problems. So we would deal with the property surrogates. And as already introduced, I will deal with the flash calculations, so the equilibrium calculations that deal with how these separate between liquid and vapor phase. The model that I want to replace is the Saft gamma mi equation of state, which basically allows us to calculate the properties of a given molecule based on constitutional groups, which is also very handy when it comes to the solvent design part. But now we want to replace it because the TP flash using the Saft gamma mi is known to be rather slow and also might have some convergence issues. And how we did that, so we sampled the South Gamma Me-based TP Flash model in the parameter region that we know is close to the processes, or in the bounds of the process optimization that we have. We then curated and basically curated our data using Python, and used the PyTorch framework to train our machine learning surrogate, which is an artificial neural network that we then translated to C++ in libtorch, which is basically the C++ equivalent of PyTorch. So we can reintroduce it into our process model, which is calculated using the process simulation software GPROMS. And now we look a little bit more into the details of our ANN architectures and look at some first results of that, or some results here. So the considered mixture is water, MEA, CO2, and nitrogen, which is like practically the basic mixture that we have to consider when dealing with these kind of plants. And since we want to replace our equilibrium calculations that would previously be calculated using TP Flash algorithms, the first idea was to use features for the ANN that are the variables that we would usually use to calculate the Flash calculations. So we use the temperature, the pressure, and the global composition. So how much water molecules do we have in total, how much MEA molecules we have in total, and so on. We use 2 hidden layers with 20 nodes in each layer here. And a rather important detail here is that we use the LU activation function, because the more commonly, or I think most commonly used activation function ReLU has the problem that when we want to calculate the derivatives, this gives us non-smooth derivatives. And since the optimizer that we want to use to optimize the process later is a gradient-based or derivative-based optimizer, having non-smooth derivatives might lead to the optimizer getting stuck or not even being able to converge. But changing or using a smooth or differentiable activation function such as LU deals with this kind of problem. And as the output, as expected, we want to know how do our molecules distribute between the liquid phase here indicated by an X and the vapor phase here indicated by an Y. And to show you some results of the ANN is that we obviously, one of the most important properties that we want to calculate is how much of our CO2 is stored or is basically absorbed in the liquid phase in the absorber. So the liquid phase CO2 mole fraction is very important. And you can see that we have quite excellent results shown here in the parity plot with SAFT on the ground truth model on the x-axis and our ANN on the y-axis. Another very important property is how our MEA would distribute or would leave into the vapor phase, because that's also a known issue that we can leave some of our solvents to the vapor phase and therefore to the environment. And that basically increases our cost because all the solvent that we lose needs to be replaced. And then, so we will have to be very accurate if we later want to optimize the process in regards of costs. And that already brings me to the first study that we did here. Here we performed an exemplarity optimization of the process, where the initial conditions are here indicated by the 1. The molecule indicates the SAFT result, like the results that we have from using our ground truth model in the process, the SAFT model, and the symbol indicating the ANN shows the results for the ANN. We start with the lean loading of 0.25 and an absorber stage height of 1.8 meters, desorber pressure of 0.181 megapascals, which is roughly 1.8 bars, an absorber temperature of 313 Kelvin. And if we now calculate the objective function at this initial point, we get values of 36.09 for our SAFT model and $35.55 million per year for our ANN. And the objective function that we want to optimize are the total annualized costs, which basically include the operating cost on the one side, but also the investment costs that we have to start the process or to build the process plant in the first place, stretched over plant lives that we assume to be 25 years. We now perform the optimization. We compare the results as a point that we achieved, and we see that the lean loading results here are relatively close together with 0.1 something for SAFT and the ANN. The stage height is also very close together, very close to 3 meters. The desorber pressure appears to be very close, but considering the scale, there is some, like, because it's megapascal that we look at, there is a slight difference here, and the absorber temperature is practically on its lower bound, which means that it basically either is already at the optimum or it wants to go lower than that. If we now consider the results that we got for the objective function, we see that for the SAFT-based model, we get $32.09 million per year, and for the ANN-based model, we get roughly $33 million per year, which is a slight difference. But considering that the point that tells us that the point in the variable space is relatively close together and goes in the correct direction, the accuracy, like we deem the accuracy, actually good enough. And since the first objective that I introduced was to increase the speed, obviously interesting would be how long the optimization took. And you can, we see here that for the SAFT-based or the ground truth-based process model, we have an optimization time of 230 seconds. And for the ANN-based model, we have an optimization time of 94 seconds. This alone, or these numbers, really make it a bit hard to believe that the time investment that we needed to develop that are really worth it. But you have to consider that these kind of process optimizations have been repeatedly done in an integrated solvent and process design problem, and this can easily give us the advantage that we wanted in the later stages. And also, one of the other points that I wanted to investigate are the robustnesses of our model. And here, since we are not yet in the solvent design space, I looked into that by sampling a space, like sampling some points of our variables where we know there are some feasibility issues, such as the desorber pressure and the lean loading, and then saw how well each process model is able to sample the space and how big the feasible region in this combined parameter space are. And here you can see the results for our ground truth or SAFT-based model, with the desorber pressure on the x-axis and the lean loading on the y-axis. The very small points, small back points here show failed simulations, whereas the colored bigger points show the feasible solutions, where the color should indicate the objective function, whereas here the objective is very close together compared to the scale, so they look rather similar. And the dashed red line shows us the convex hull, which should give us an idea about the feasible region of the process. And if we now compare that to the results that we get using our machine learning surrogate, we see that we first cover a wider range of our objective function value, as well as a slightly higher or bigger space of our parameters that we wanted to sample. We now overlay both feasible regions. We actually see the effect in a better way, in a better comparison. And what we learn is that it appears that the machine learning surrogate is or tends to be more robust, especially close to infeasible regions of the process, which actually makes is very promising, because especially in the solvent design problems, we have to initialize our process sometimes at points where we don't know where we are and how close we are to the actual objective function. And as sometimes we need to find a feasible point first, and increasing the infeasible region basically will give us an advantage when we move on there. Another interesting point here was the sampling time. So the SAFT-based model took more than 48 hours, like basically more than 2 days, to finish the sampling with the same amount of points, whereas the machine learning-based model was finished in 5 hours. So what that actually shows that once we move out of the feasible region, even the speed advantage of our machine learning surrogate can get up to 10 times, or roughly 10 times of that we have using our SAFT-based model. And that already brings me to the end of my talk. So just to conclude very briefly, we developed a machine learning surrogate that replaces SAFT-based flash calculations in a process model for amine-based carbon capture. And we could show that it is faster and debatably more robust than this, the ground truth model or the SAFT model. And just to give you a small outlook, I mean, I was talking about it quite a lot during my talk, so it's rather obvious that we want to move on to use these machine learning surrogates in the overall solvent design, solvent and process design problems. And then we want to see how that gives us an edge compared to the ground truth model. And also at this stage, we want to include more property surrogates that my colleagues of the work package 2 are working on, such as surface tension and viscosity. I'd like to thank you very much for your attention. I'd like to thank the EcoAI-WP2 team. I'd like to thank the UKRI for funding our research, as well as the organizing committee and today's organizers for hosting this webinar. And now I'm open for questions. Thank you very much. Hello.
Okay. Thank you. Thank you, Florian, for your presentation. That was really astonishing and excellent. So I can see there are some questions in the chat box. So if you don't mind, answer the first question, which is for the typicalized surrogate using ANN, do you check if the predicted X and Y fulfill a feasible mass balance?
Thank you very much for that question. Actually, we do not really have to do that because we somehow use how the process itself calculates the mass balance to the process itself does not need to need all the compositions at once to be calculated to such that the mass balance is fulfilled. So we actually also do not predict all of the X and Y's of the mass balance. So we do not check if that is the case, but actually we also don't need to because the process itself will deal with that problem. Ahmed,
yeah.
I think you are.
Sorry, yeah. So can I ask a follow-up question on this small one? So you are not predicting everything and you delegated the mass balance to the process based model, so to the standard thing. But in what you have predicted, is there any physical constraints which have to be satisfied, or is validity checks in the part you have predicted?
Well, obviously we can check, and that's something that I did. We check with the objective function itself, right? So if the objective or the process itself gives us something that is feasible or makes sense, we can be more or less sure that the surrogate makes sense. And also we check that the surrogates do not go below 0, for example. So the mass a fraction cannot be above 1 itself or below 0, and that's something that is actually fulfilled by our surrogates. And above that, there is no constraint in the training itself, but they are still fulfilling it, which is, I guess, based on the data that we use, because none really stretches about the whole range of fractions, right? None of our predictions are really going from 0 to 1.
Thank you.
I think I was a bit fast.
Yeah, no, it's very good. I really like the presentation. I can follow up with other questions if Amine doesn't have any questions. So the question is about adding training data on the fly. Have you thought about that?
You mean in further iterations of the solvent? Yeah, we thought about that. We actually, I already have some first results on that, where we basically trained our first ANN very thoroughly for the MEA part. And then once we know the next molecule, we just sample a fewer amounts of data points and retrain, basically transfer learn the already existing ANN. And that has promising results. We simply don't know yet, since we have to introduce it into the process model and then have to see how that really works out with the accuracy, because obviously here are some drawbacks in terms of accuracy. But we do not yet know how that translates to the process model and how that, the process design problem. But yeah, that's definitely one idea. The other idea would be to train a rather bigger surrogate that is also able to predict all these properties, or all these basically all these properties based on groups such as the underlying model does, like the soft equation of state does, which is also one of the pathways that my colleagues in the WP2 are following. So there is more than one way to do it, but yeah, transfer learning would be the one that I would try first.
Very, very good. Thank you for the comprehensive answer. I really like this future research direction. I have one more comment if we don't have, if the chair allows me. So can you tell us about the technical challenge of porting your model from an integrated, like usually it is Python based, you are now have ported it into C++ and embedded it in a whole package, which is commercial package, in my understanding. And then this kind of like twinning of machine learning and standard process-based modeling, was that like what kind of challenges have you faced? Because it's somehow super powerful, in my opinion.
So what worked really well and was changing from Python to C++, because basically PyTorch has a C++ equivalent, which is libtorch, and you can basically use the pre-trained model, simply transfer it. It took me quite a while because I wasn't experienced in programming in C++, but the thing itself was rather simple. And the software package, so gproms, also offers the possibility to introduce foreign code, like foreign functionalities, into the process, which was a bit challenging though, because you will have to understand how the connection works and so on. I think overall it took me roughly 2 weeks to implement it, so that works rather well. And theoretically, it's also possible to use Python code, so that it has some features, like some possibilities to directly use the trained model from Python, but these are slower, slightly slower.
Yeah, definitely slower, but the training still happens in Python. You serialize the model, and then do you use generated code in libtorch, or you rewrite? How do you?
Actually, no, I do not have to I use this serialized model that basically just uses these, I think they are called pickled files. And then I do not have to rewrite the model architecture. It basically just takes a model based on these files and then gives us what I want to calculate. And this is actually very powerful though. You can easily transfer models like that and calculate everything you need. Derivatives, like for me, one of the main problems was to calculate the derivatives because they are definitely needed. Like being able to calculate analytical derivatives gives us an advantage when we have gradient-based optimizers. So that's the main advantage of our machine learning model, or at least in the ANN. So doing that easily in the transferred version was very important, and it worked very well. Yeah.
Thank you.
Thank you for the questions.
So if you don't have any question, Ahmed, because for sake of time. Thank you for all your questions. That was so good and that was so narrative. Yeah, thank you so much, Florian, once again for your presentation, and hope all the best in your future research.
Yeah, thank you very much.
Thank you. So the second presenter for today is Dr. Mengjia Zhu. She received a bachelor degree from chemical engineering in University of Washington and Master of Science in Chemical Engineering from Imperial College London. She did her PhD in System Science at IMT School of Advanced Studies, Lucia, if I read correctly. She is currently working as a postdoctoral research associate at the University of Manchester. Her current research interests include black box optimization and control, with particular emphasis on active preference and safe learning. Thank you for joining today, Mengjia, and floor is yours.
Mengjia, you're muted. You need to unmute yourself.
Sorry about that.
No problem. The floor is yours.
Yeah. Okay. Yeah. Hello, everyone. Thank you for joining this session. So today I will be presenting our project titled the Optimization-Based Operational Space Design for Effective Bioprocess Performance Under Uncertainty. This work is collaborated with Olive and Sam and supervised by Dr. Dongda Zhang. So first of all, I want to give an overview of the presentation today. First, I will discuss the motivation for the project, then the target problem and the project goals, as well as some main assumptions will be introduced. Following that, the problem formulation and the proposed solution methods will be discussed. And then the effectiveness of the proposed solution method will be demonstrated via an illustrative case study. At the end, I will also give an overview of the AI for aerobic digestion project. So for bioprocess industries, including pharmaceuticals, biotechnology, and food production, it always often rely heavily on biological systems to produce products of consistent quality and yield. This is to minimize waste and enhance economics. However, biological processes are inherently variable due to complex and often poorly understood interactions within living organisms. We often utilize process optimization and quality control techniques to control the process. In order to do that, often we perform a system identification approach for which we will develop a mathematical model that describes the system dynamics. With that model developed, we can then develop relevant control strategies. However, a lot of time for industrial applications, if we want to do real-time feedback control, it can be very expensive or sometimes impractical. It is because sometimes it may be we have limited computational capacity. Also, it may be difficult to do real-time implementations. With that being said, we want to provide a guideline in terms of operational space in this project. Specifically, we want to develop this operational space such that the operator can be on track without the need for embedded or real-time control systems. On this slide, I show the target problem that we want to solve. Specifically, in this project, we will focus on fed batch bioprocess subject to parameter uncertainties involved in system identification step. The goal of the project is to find an operational space for a given reference control input trajectory. Specifically, if the control input is within this identified operational space, regardless of the parameter uncertainties, we should be able to achieve satisfactory performances of the process. Some main assumptions are listed on this slide. Specifically, we assume that the range of the uncertainty parameters is known, and also the initial state is also known. Also, it is the same across different batches, and the desired output as well as the acceptable bounds are known as well. We assume that the control input can be time varying and the reference trajectory is known. It can either be calculated or provided based on the nominal operations. So the operational space we want to define can be time varying as well. And we assume that we operate on a fixed time horizon and the system dynamics are known. With that, we want to show now the problem formulation. Specifically, we will consider the dynamic system of a fed batch bioprocess. It can involve multiple states, and it will be modeled with the following ordinary differential equations. Here, X is the vector that collects all the states. For example, for a bioprocess, it may involve biomass concentration, substrate concentration, and X dot is their corresponding time derivatives. And U is the control inputs. For example, it can be feed rate or temperature. Here we use P to collect all the parameters that are subject to bounded uncertainties, and theta is used to collect all the fixed parameters. Additionally, we also assume that full state observation is possible. In the following, I will discuss the proposed solution methods. Specifically, we will first discretize the time horizon into n intervals, and in each interval, we implement a piecewise constant control. Then we reformulate the problem as an optimization problem with the objective to maximize the operational space. In the meantime, we also want to satisfy all the system constraints. For example, we need to respect the system dynamics. Here, with the discretized system, the next state can be calculated based on the integration of the system. You may use a selected numerical integrator to obtain the state. And also, the initial state should be respected. Some path constraints and terminal constraints may also be involved. Examples of path constraint can be the rate of change of substrate concentration should not exceed certain value to avoid the process being unstable. Also, some terminal constraints can be, for example, the final production should be higher than some target value. Additionally, we want the operation to be within our defined operational region, and these upper and lower bounds are the ones that we want to determine later. And also the control should be positive to be physically valid. The solution involves certain steps. First, we want to define the reference or the nominal trajectory. This can either be given based on the nominal operation or can be identified using the optimal control strategy. In this case, we can first assign the uncertainty parameters using their nominal values. And then we formulate the optimization problem, which we will discuss in the following slides to identify the lower and upper bounds for the control. In this case, we will use scenario optimization with uncertainty samples drawn from their relevant distributions. And lastly, in order to validate the identified operational space, we will sample from the uncertainty parameters on a larger test set and then test if there is any violations. For the optimization algorithm, to identify the bounds, we implement a two-stage operation step. In the first stage, we want to maximize the difference between the nominal operation trajectory and the corresponding lower and upper bounds. An example for the lower bounds identification is shown on these slides here. Specifically, we want to maximize the minimum distance between the original nominal operation and the identified bounds. In this case, we selected the maximize the minimum distance instead of maximize the sum of distance is because if we try to just using the sum distance, there may be cases that you may find the deviations is collected into certain intervals while with the rest of them being very close to the nominal one. Such bounds, as shown on the figure on the right-hand side, is less useful for the operation. And in the second stage, since we have already defined a general shape of the operational region in the first step, in further stage, we can now trying to minimize the difference between the current best bounds and the newly identified ones so that we can maintain the operational space as much as possible and limit the adjustments. In this case, we can now use the minimize of the sum of distance. An example is shown here for the lower bounds identification. We show the proposed methods on a case study. Specifically, we apply it on a fermentation process as shown on the slide. The kinetic model of the process is taken from this paper. And here the state variables are X, S, and P, which are the concentration of biomass, substrate, and product. Some relevant parameters are also listed on the slide. We converted the kinetic model to a fat match model by introducing the feed flow rate, as shown in the first equation here. And we adapted the rest equations accordingly. We can collect the model into a compact form so that it's consistent with our problem formulation. In this case, the uncertainty parameters are listed here. And our control goal is to achieve a satisfactory mass production of the final product at the end of time horizon. Specifically, we want the mass production to exceed a certain lower target. And the initial condition as well as the parameter values are listed here. We identify this operational space by applying our approach. Here you can see that operational space is increasing as time goes. This is because we also implemented an additional constraint that we want the operational space to increase as time goes. The rationale behind it is that if we adhere to the operational space initially, we have more variability at the end as time goes. And this shows our flexibility of the approach. For example, if you know at a certain time step, the operation is critical and you want the variation to be minimal, you can impose the relevant constraints to enforce that. We also validated the operational space using a large testing sample, in this case, 10,000. And the parameters and as well as the operation control trajectory are sampled based on from their uncertainty bounds. And here the leftmost bar indicates the terminal constraint. And as you can see, there's no violation. In conclusion, in this project, we explored an operation-based approach to improve bioprocess performance under uncertainty. By defining an operational space for bioprocess control, we offer a practical solution that can minimize the need for real-time adjustments and also making it more economically feasible for industrial applications. At the end, I also want to look at the broader context. Specifically, this research is part of a larger AI for Net Zero initiative. The project focusing on enhanced biogas production, and the project aims to develop tools that can increase the flexibility and the profitability of the aerobic digestion process. Specifically, we want to adjust both feedstock and the microbial productivity while leveraging optimization and optimization-based models and real-time set operations. The project involves different universities and collaborative industrial partners as displayed on these slides. That's all for my presentation, and thank you for your attention. I'm now happy to answer any questions you may have. Thanks.
Thank you. Amine, you're muted.
Yeah. Thank you, Mengjia, for your presentation. That was crystal clear, and yeah, that's amazing. So if anyone in the audience have any question, please leave their comment on the chat box so we can ask Mengjia about it. Meanwhile, if Ahmed, if you have any question, please feel free to ask.
I always have questions. Excellent presentation, Mengjia. There are a lot of details. I caught only part of it. And one of the questions which comes to my mind are the limitations of the assumption. For example, you have known and fixed initial conditions. Are these strong assumptions? Other assumption is like full observability of the system. How do you think of the limitations imposed by these assumptions?
Yeah, so mainly like because this approach will rely heavily on a system identification step, and these assumptions is actually also mainly imposed for the system identification step. So if we have like a proper if we have a proper system model, then this assumption can be alleviated. But usually, in order to have a good system model, these assumptions are often necessary. But of course, there is like different techniques. For example, you can use the common filter and different ways to help alleviate this. But just to simplify the assumption for this current project, we decide to just assume that. But it's definitely valid. Yeah.
Thank you. And then could you please link that to the Monte Carlo, because I lost you when you When you move to the Monte Carlo analysis, that was each sample of the Monte Carlo analysis have these set of assumptions. Is that correct understanding or?
Yes. So basically, we assume that after the system identification step, like your parameters can still like be uncertain and may vary between a range, and you can like sample from these ranges to realize different trajectories of the system, and then the trajectory is also like sampled from the identified operational space. And then if you implement this operational space with a model, and then you can still achieve the desired goal, basically. Yeah.
Fair enough. I'm checking and putting an eye on the questions. No questions so far came about. And if you have questions, please interject. When I saw the you are applying discretize, and then you get the sensitivity, right? There is an alternative approach where you get the sensitivity and then discretize in time specifically. And I kind of like, while you were talking, I would just remembered that, or kind of like came to my mind a paper which came 5 years ago about neural ordinary differential equations from the University of Toronto. I think it was in 2019 or 2018, where they rely on the machinery of automatic differentiation to accelerate somehow system identification of ODEs for the machine learning community. They were not fully aware what chemical engineers do and a lot of computational scientists do on a daily basis. Have you kind of crossed that to see what's in that literature in comparison to what's in your literature?
Yeah, I checked some of the relevant ones, and so main difference is like, for example, here, even though like it's uncertain, so once you start to implement, it's fixed across the whole time horizon. So if we try to use, for example, the interval like bound propagation, which will consider all the scenarios, it will be like overly conservative, and then it will not be really practically usable. So in this case, even though like it's not fully robust because it's still based on stochastic optimization, scenario-based optimization. However, it's we assume like it's still more valid for the industrial applications. Yeah.
Thank you so much.
Yeah, thank you.
I mean, your turn for question.
Yeah, thank you for Ahmed for all these accurate and narrow questions. Also, a question about the this accuracy and the scenario. How you generate this scenario and how wide this scenario, and what is the background about this scenario, if you could explain.
Yeah, so basically, in order to like increase the robustness, we will try to sample as many as possible. But then in order like with more samples, if you want to run the optimization once, it will be like very computational heavy. Some technical details that I didn't cover is like we basically separated into different stages, so that in the first stage, we will put like for example, 10 samples or 100 samples based on the computation capacity of your computer, that you calculate the general shape of the operational space so that it can be still good. And then you feed more samples in, and then you can refine the bound so that you narrow it down because you have to fulfill all the requirements. So that like later on, if in your validation step, you find some is not fulfilled, you can refeed this back into the process, which is still like, so that it's like still like self-improving step instead of like feeding it in one go, and then you have to rerun the whole thing if you find some issues. That's some main advantage that I didn't cover. Yeah, sorry about that. Yeah.
That's great. Yeah. And what about computational? How big it is computational time, and if it's too much, what's the way to reduce this time, computational time?
Yeah, so like if you want to, for example, in this case, I identify the bounds based on 1,000 samples, scenarios. And basically, I divided into 100 groups. Each of them just need to solve 10 scenarios, which is very computationally light. And with that, so it's for this one, I think it's about like 20 seconds. It was able to solve all the 1,000 scenarios. And basically, I think it's nice that you can do it stage-wise. Yeah.
That's great. So you don't have any scenario reduction after generation, I assume, yeah?
Yeah, so basically, like the reason for including the scenario is trying to mix the identified operational space as robust as possible, so that when later you can, instead of feedback control, you can just show the operational space to the operator. Like as long as you don't like vary outside of this operational space, you should be more or less safe. Yeah.
And how many parameters you can use in this scenario base? I mean, how you can modify?
Yeah, of course, like it has issues similar to the scenario optimization. Like as your dimension increases, it can be like much more challenging to decide like what samples you want to include. But like right now, it's really depends on like how complicated and how large is your like allowed sampling region, and also, yeah, I would say it's case dependent, but more or less, I think it's. With this stage-based approach, you can accommodate more samples than you would usually do. Yeah. Mm-hmm.
Awesome. Thank you.
Thank you.
We don't have any other questions. I would like to thank you so much, Mengjia, and I would like to ask you a question about interacting with the bigger team and with the industrial partner. I assume that you are more on the mathematical side. What is there anything you could share with us about this experience?
Yeah, it was it's a very nice ongoing project and collaboration. So because we have a lot of partners, and it's a different experience because previously I usually work with simulated data, and if the case study we showed here is the simulated data, but we are also working on the data from shared by our industrial partners as well as laboratory partners. So it's nice to work with real data. Of course, there's difficulties with real data because it's has more like variations, uncertainties, and sometimes the data is not recorded, and so basically it's a good learning experience for for us, like only working on the, let's say, like the systems, usually like simulated systems. Yeah.
Thank you for sharing.
So if there is no question, let me see. Yeah, there is no question in chat box. I could conclude this this talk. Thank you again, Mengjia, for your presentation, and thank you, Ahmed, for your helping for this session. I wanted to notice all audience about the ongoing conference AI for Net Zero conferences. The registration is now open. You can find information through the link that will be going to subtitle here, and also on the subscription you can find it later on. Please join us for this conference. It's placed in 16 to 19 of December at the University of Exeter. We'll host the 4 days event, bringing together all leading experts and high-profile speakers to discuss how AI can drive meaningful progress toward achieving net zero by 2050. So if you have any research, any topic that you would like to share with others, please have a look at the website and submit your abstract if you'd like to. And yeah, hopefully see you there in the conference.
And I would like to take the opportunity to announce the next session as well, which is next Tuesday at 2 p.m. GMT time, because we changed the hour. In the next session, we will host Dr. Gaga Wen from Imperial College London. She will present machine learning applications in CO2 geological storage for net zero. So please tune in and join us next week. And thank you, Amine, for co-chairing, and thanks to our speaker. And see you next week.
Thanks very much. See you next week.